This is test 2 review, Math 2331 linear algebra. This test review, it covers here 3-1, 3-2, 3-3, and then 5-1, 5-2, and 5-3, these sections from our textbook. So we will begin with number 1. This is quite a lengthy test review, but it's wonderful for us. Number 1, well, we're given a matrix A. It has 4 rows and 5 columns, and we're also told the reduced row echelon form. A and B, we want to find a basis for the kernel of A and a basis for the image of A. So let's get started. Letter A. Well, you see, let's look at our reduced row echelon form. We have leading 1, leading 1, leading 1. We also have free variable, say T, and free variable, say R. So if I'm trying to solve for an element in the kernel, right, this is really the solutions to AX equals 0, I would just say let X2 be T and X5 be R. And then we see X1, this is minus 3T minus 7R. We have X3, this is just minus 9R. And then X4 will be positive 6R. So a general element in the kernel, I can write this, and then from this, I'll be able to write down a basis. Well, X1 is minus 3T minus 7R. X2 is T. Then X3, we see minus 9R. X4, 6R. And X5 is R. Immediately, we can write down our answer. We can write down a basis for the kernel. There will be 2 elements in this basis because we have 2 free variables. So you notice if I look in this vector here, I have T times minus 3, 1, 0, 0, 0. So that would be minus 3, 1, 0, 0, 0. And then I have R times minus 7, 0, minus 9, 6, 1. So this is my answer to the first one. This is my basis for the kernel of A. Well, the image of A, to find a basis for that, it's shorter. What I do, you see I have leading ones in columns 1, 3, and 4 in the reduced row echelon form. So I just pull off those columns in my original matrix. The basis for the image of A, well, it has 3 elements because I have 3 leading ones. We use the first column, which is 1, 2, 3, 2. We use the third column, which is 1, 1, 2, 2. And we also use the fourth column, 2, 3, 7, 4. This is my basis for the image of A. Now, we're not finished with number 1. The next question, we want to find a basis for the orthogonal complement of the kernel of A. So let's go back and look at our matrices for a second, okay? What the orthogonal complement of the kernel of A? Well, we know the kernel of A, this matrix, and the kernel of the reduced row echelon form are the same. And what else do we know? We know the orthogonal complement of the kernel of A. This is the row space of A. So what this is asking for is a basis for the row space of A, but this is also equal to the row space of the reduced row echelon form of A. Okay, so let's just write down a basis. In fact, once we go to reduced row echelon form, which is here, I can just pull off the non-zero rows. So I would use this row, and this row. Now, this is not your only option. You see, I could also use the first 3 rows of matrix A because I can tell the last row, let's see, you see it's 2 times the first. But I'll just use the first 3 rows in the reduced row echelon form of A. Maybe let's take a screenshot and include this on the next page. I'll put it right there so we can see what we are working with. So I have 3 elements. The first is this row, 1, 3, 0, 0, 7. And then I have 0, 0, 109. Finally, I have 3 zeros followed by 1 minus 6. This would be my answer in this one, letter C. Letter D just asks us a bunch of dimensions, and especially looking at the reduced row echelon form here, we can figure them all out without going back to our previous page. So maybe I'll start down here with the rank of the matrix, because that will be our answer in multiple questions here. So the rank of this matrix you see is 3, number of leading ones in the reduced row echelon form. But the rank of A transpose, well, that's always the same as the rank of A. So this is also 3. This would be the dimension of the image. This would be the dimension of the row space. In fact, here's a basis for the row space. We see 3 elements. Now, for the kernel, you see, this would be, we have 5 columns. It would be 5 minus 3 or 2. But another way you can answer this is just by free variable, free variable. There's 2 of them. Now, one more. This says the dimension of the orthogonal complement of the image of A. Well, you notice the image of A sits inside R4, right? Each column is in R4. And so the image is a subspace of R4. The image is a subspace of dimension 3. And so its orthogonal complement has dimension 4 minus 3, which is 1. We move on to number 2, justify our answers. Always, this is important. First one, is this collection a basis for R3? Well, let's figure out if this collection is literally independent. And then if so, the answer will be yes. We can put these vectors as columns in a matrix. We have square root 3, 0, 0, 0, 1, 1, 0, 0, 5. And I really don't have too much to do here. Let's take minus row 2 added to row 3. When I do, I get this. You notice this is in row echelon form, but from this we see the rank is 3. And this says that these vectors are linearly independent. Whenever you have a collection of vectors and you put them as columns in a matrix, and then if that matrix has rank equal to the number of columns, you know you have linearly independent vectors. But this says the vectors are linearly independent. Now, we also know the dimension of R3 is 3. And so any collection of linearly independent vectors, 3 of them in R3, will be a basis. So the answer is yes. Because we have the right number as dimension, and we have justified these vectors are linearly independent. Okay, again, we have this time 3 vectors in R4, and we want to know, are these vectors independent? Okay, great. I will do this one differently, just to show different techniques. So if we have C1 times this first vector, which is 1, 0, 0, 0, and then plus C2 times the second vector, which is 0, 2, 0, 0, plus C3 times the third vector, which is 0, 8, 1, 1, equals 0. Well, this is really, we have 4 lines here. And in particular, if you look at, say, line 1 of this linear system, gives us C1 must be 0. Now, once C1 is 0, say, well, even before knowing this, you can look at line 4, for example, and this would say that C3, 1 times C3 must be 0. Now we have C1 is 0, we have C3 is 0, and for example, just look at line 2. This says 2C2 plus 8 times 0 must be 0, and we conclude that C2 is 0. Okay, now, did you have to do it this way? No, you didn't. You could have just put these as columns in a matrix and transform to row echelon form. and seeing that the rank was 3. This would say the columns are independent. But I wanted to illustrate 2 different ways of showing vectors are independent. So part A, the answer is yes. Letter B. Is this a basis? This collection of 3 vectors, is this a basis for R4? B is no. B is no. So this one is no. We do not have a basis for R4. And the reason is we have 3 vectors cannot span R4 because the dimension is 4. So 3 vectors cannot span R4. And the final question, letter C, is this collection a basis for the span of those 3 vectors? And that answer is yes. Letter C is yes, because we already showed they're independent. And then I'm saying that they span some vector space. So independent plus span, this gives basis. Maybe I should say, instead of plus, I would say and, like this. Okay, so this is our justification on 2B. Which of the following subsets of R3 are subspaces? And I'll say one of them is yes and one of them is no. So the first one, letter A, is the yes. This is a subspace. Now, justify. What would be the reason? Well, you notice that this collection is the kernel of a matrix. The matrix would be where you just have 1, 1, 1, because if you take this matrix here and you multiply this by, say, x1, x2, x3, a vector, right? x1, x2, x3, you get exactly this expression. And the kernel of a matrix is always a subspace. This set is exactly the kernel of a matrix. Yes, it is a subspace. Now, part B, the answer is no. And in general, guidance I can give you, we saw an example like this in class, is when you see inequalities, okay, you should think the answer is no. When you see inequalities, even if, so you see this collection contains 0, for example, usually it's the scalar multiplying that fails. And to justify, for example, find something in this set, well, we want what? X3 to be the biggest. Okay, this vector is in the set, but minus 1 times this vector, or minus 2 times this vector, minus 100 times this vector is not. This is just the vector 0, 0, minus 1. This is not in the set because x3 is not bigger than or equal to x2. This is not in the set. And this justifies that this collection is not a subspace. Let's move on. Number 4. In fact, this is similar to the last one we did, but let me give you a piece of advice. If you see a question, is some collection of vectors a subspace? And then you have parts B and C that ask you its dimension and ask you the dimension of the orthogonal complement, probably the answer to A is yes. Okay, that's just a piece of advice. So as I mentioned, the answer is yes. And how could we justify this though? And in fact, the justification is what will help us with B. So I can rewrite these conditions as x1 is 0, and then say x2 minus x3 is 0. And you notice that V is the kernel of a matrix. Okay, once again, we have a kernel of a matrix. The matrix is here. Okay, this says x1 is 0, and then here, this says x2 minus x3 is 0, right? You can think about these equations and what they say. So that's our justification. In fact, we have a subspace. Now this can help us, you see, because in B, we need the dimension. So this matrix has rank 2. And so if you think, for instance, the rank nullity, we have 3 columns. The dimension of V is 1. The dimension of the orthogonal complement of V, well, V sits inside R3. And so the dimension of the orthogonal complement of V sits inside R3. It would be 3 minus the dimension of V, which is 2. This is the answer to letter C. Number 5, we have 2 parts. Okay, part A, we want to find the angle between these 2 vectors in R4. So we use the fact that theta is the cosine inverse of, well, if I label, say I label this V and this W, then the angle between them would be cosine inverse of V dot W over the length of V times the length of W. Okay, so what we need to do is just calculate all these quantities and then figure out what is that the cosine of. Okay, we have V dot W, which is 1 times minus 1, okay, plus 1 times minus 1, plus 0 and 0, we get -2. And then we need the length of V, we need the length of W. The length of V is, well, it's a square root, and we have 1 plus 1 plus the square root of 2 squared, which is 2. So this is the square root of 4. The length of V is 2. And the length of W, okay, this is the last piece that we need before we can figure out the cosine of the angle. This is just, okay, we take -1 squared plus -1 squared. Well, maybe I'll put 0. It's fine. The length of W is the square root of 2. Very nice. So theta, here we go. This is the cosine inverse of, we have -2 divided by 2 times the square root of 2. And, well, this we can actually do. This is cosine inverse. We have -1 over square root 2, or you could also write it this way, square root 2 over 2. And now you can start to see, okay, it says the reference angle is pi over 4. Cosine inverse gives you something between 0 here and pi, but it's negative, so it's going to be here, right? Cosine is negative is what I meant. So this is 3 pi over 4. Theta is 3 pi over 4. This is the angle between these 2 vectors. Okay, fantastic. Letter B. For what values of k are these 2 vectors perpendicular? Well, perpendicular just means that their dot product is 0. And so if we take, okay, again, I don't have these labeled. Maybe this is vector A and this is vector B. If I take A dot B, I get 2 times 1 plus 3k, and then plus 5 times -1. And altogether, this is -3 plus 3k. Okay, this is the dot product of A and B. Now, we want these to be perpendicular. So this would say their dot product is 0. And you see, we get 3k is 3. I'll put it here. 3k is 3, or equivalently, we see k as 1. But this is our answer to letter B. Now we have a question that involves orthogonal projection and orthonormal basis. This question I found off a very recent final from this course. I think it's super cool. So here we go. We have some subspace V of R4, and we have these 3 vectors, and we're told they're an orthonormal basis for V. Of course, you could check that they're orthonormal. Just calculate, if you wanted to, calculate the length. And for each one, you will get 1. And if you take in dot product any 2 of them, you get 0. Okay, it's not a bad exercise to check. So let's begin the question though. Part A, it says, is this vector V4 in the orthogonal complement of V? So this subspace, well, a vector is in this subspace provided it is orthogonal to every single vector in capital V. But that's equivalent to saying that vector is orthogonal to a basis for V. So we just need to check. So we can check, is V4, so this restated says, is V4 orthogonal to V1, V2, and V3? Okay, so let's just check. We take V4 dotted with V1, and we need V4 dotted with V2, and we need V4 dotted with V3. What do we get here? Okay. Well, you see here, take this and dot this. We have plus and minus of the same thing, which is 1 over 2 square root 2. This is 1 over 2 square root 2 minus 1 over 2 square root 2. This is 0. Now we take V4 and V2. And you notice, again, we have the same thing, except the negative sign. I could even copy and paste, except the negative sign should be on the first one. So this would be a minus here and a plus here if we go in order. And again, you see 0. Now we take this vector and we dot product here. But you notice we have minus a fourth, plus a fourth, minus a fourth, plus a fourth. We have minus a fourth, plus a fourth, minus a fourth, plus a fourth. We get 0. So the answer in A is yes. Okay, just because, as I mentioned, V4 dot, each vector in this basis is 0. Therefore, V4 is in the orthogonal complement of V. Very nice. Now, let's move on. We are told Y is a vector in R4, and it satisfies some things, okay? In particular, Y dot V1 is the square root of 2. Y dot V2 is 2 times the square root of 2. Y dot V3 is 4, and Y dot V4 is 2. Just knowing this and not actually having our hands on Y, although we will when we do part II, but just knowing this, we should find the projection of Y onto V, and similarly find Y itself, okay? Well, you have to remember, first of all, we'll do the projection, okay? Then I will talk about Y itself. Projection onto V of vector Y. Well, the formula you take Y dot V1 times V1, right? Y dot V2 times V2, and then Y dot V3 times V3. This is exactly how we calculate projection when you have an orthonormal basis for your subspace. So this would be the square root of 2 times this vector. Then we have 2 square root of 2 times the next vector, and finally we have 4 times the V3, the third vector, which is minus 1/2, minus 1/2, 1/2, and 1/2. Now we just add all of these up. We don't want to leave our final answer like this. We actually want to know what are the components of this vector. So we add everything up. Okay, well, you notice when you multiply this, we just have 1, 0, 1, 0. And here we have 0, 2, 0, 2. And then here, the coefficient in each entry is either minus 2 or 2. This will help me as I add. The first entry, I have 1 plus 0 minus 2, negative 1. For the second component, I have 2 minus 2. 0. The third component, I have 1 plus 2, 3. And then I have 2 plus 2, which is 4. Okay, so this is my answer in letter B. This is actually, I didn't have my labeling right. This is BI. Okay, now we move on. We have BII. Okay, very nice. Well, we want y itself. We want y itself. And we have to really use our knowledge here. So the calculation is not that hard. We have to use our knowledge, right, of what we're looking at, which is why this is a cool problem. So here we have this collection, which is a basis for V. And this, you can take this vector, it's non-zero. In fact, it's also unit. So you can take this here, this before, just before, you can take this as a basis for the orthogonal complement of V. Because we know, for example, there's 3 things. V has dimension 3, and everything is inside R4. So the orthogonal complement will have dimension 1. So if we want to get the vector y itself, well, we are told the coordinates. These are all the coordinates of y with respect to the basis for R4, that is V1, V2, V3, and V4. That's exactly what we're told here. So to get y itself, as we need in letter II, maybe I will show an intermediate step here. This would be the square root of 2, V1, right? That's that coordinate. And then 2 times the square root of 2, V2 is the second coordinate for the V2 vector. And then we have 4 times V3, and then we would have 2 times vector V4. Okay, because as I mentioned, V1, V2, V3, and V4, these form an orthonormal basis for R4. Okay, and so an effect here is the coordinates. Now we just add. We can save ourselves a little bit of time because you see the first 3 terms we have already added up, right? All of this we have added up. It's this vector. So this is -1, 0, 3, and 4. And then we add what happens when we take 2 times V4. Well, it's just 1, -1, -1, and 1. So this is vector y. We get 0, -1, 2, and 5. It's kind of small. There, it's written a little nicer. This is our answer to 6BII. Okay, fantastic. Number 7. Now we have Gram-Schmidt, which is wonderful. The first question, though, 7A, asks us, is B1, B2, B3, this collection, is this a basis for the space that it spans? Well, all we need to do is figure out if this collection is linearly independent. And we can address this in more than one way, but I think the shortest way is just put these vectors as columns of a matrix, and we can perform one elementary row operation. Just take minus row 1 and add this to row 3. And when we do, we have 1, 2, 2, 0, 3, 3, and then 0, 0, 2. Okay, this is in row echelon form. You notice the rank of this matrix is 3. And so this says that vectors B1, B2, B3 are independent. Necessarily, they span W. And so the answer is yes. We have a basis. So the answer in 7A is yes. Okay, but here comes the fun. We have 7B. We want to perform the Gram-Schmidt process on this basis. So the first vector, U1, we take B1 and divide by its length. This, as we were discussing in class, this is the simplest one to calculate. So you notice that this has length, square root of 2. So I can just take 1 over the square root of 2, 0, and 1 over the square root of 2. Very nice. This is my first vector in my orthonormal basis. Next, we calculate the direction, which the component of B2, which is perpendicular really to the span of B1 or U1, same span. And how we calculate this, you take B2 minus the projection. B2 minus the projection. And if we use U1, it's unit. So you just take B2 dot U1 times U1. Okay, so this is what we take vector B2, which is 2, 3, 2. Subtract off, we have a dot product, and then times this vector U1, which is 1 over the square root of 2, 0, 1 over the square root of 2. This gives us the correct direction. But now we dot product. We have B2 dotted with U1, and you notice we get 2 over square root of 2 plus 2 over the square root of 2. So altogether we have 4 over the square root of 2. And you notice that each entry, let's see, in this vector, we have 4 over 2, 0, 4 over 2, right? So we have 2, 0, 2. That's what I'm subtracting. So this is just 0, 3, 0. And this clearly has length 3. So the second vector in my collection here, I will call U2, is, well, what we do, we take this component of B2, which is perpendicular to the line, and divide by its length. And its length is 3. So when we do, we just get this 0, 1, 0. So far, I have my first 2 vectors in my orthonormal basis, and you can check. It's always good. Take this and dot this. We have 0. Now, we move on. We have one more to calculate, which is U3. Well, we continue, right? We take this. This gives us our third direction. It's the component of B3, which is orthogonal to the span of B1 and B2, or equivalently, the span of U1 and U2. And how we calculate this, we take B3 minus the projection, which is, let's say, B3 dot U1 times U1, and then we have B3 dot U2 times U2. Okay, this is the direction. Then we will have a second step to normalize this vector. I just moved some things around to give myself more space. So we take, this is equals exactly where, I'll pick up exactly where we were. We have B3, which is 2, 3, 4. Okay, then we have a dot product, and then times U1, and another dot product times U2. And U1 is, here I have put it in black, it's 1 over the square root of 2, 0, 1 over the square root of 2. And U2, this is just 0, 1, 0. Okay, fantastic. Now there's a minus sign, dot product, minus sign, and dot product. Now we can calculate. So we take this, first of all, and we dot product with this vector. And when we do, we get 4 plus 2, which is 6 over the square root of 2. We have 6 over the square root of 2. Then, now we need this, B3 dot U2. Well, here's B3, and here's U2. And you notice we just get 3 times 1. So we have 3. Now we just have to add these 3 vectors, or this vector minus this one minus this one. We will have the right direction for this third vector in our orthonormal basis. So here you notice the first entry, we have 2. This is 6 over 2, which is 3. So altogether we have 2 minus 3 minus 0. This is -1. Very nice. Next entry, we have 3. Here's minus 0 and minus 3. We have 0. And finally, we have 4. Let's see, this is 6 over 2, which is 3. So 4 minus 3 minus 0, we have 1. And you notice this also has, maybe I should write this just as a comment, the length of this vector is the square root of 2. So my final vector, u3, we take this component of b3, which was perpendicular to the span of u1 and u2, and we divide by its length. This is how the Gram-Schmidt process goes. So we have minus 1 over the square root of 2, 0, and positive 1 over the square root of 2. So my orthonormal basis for W, maybe I will just write this at the top. My new basis, so for 7b, my new basis is u1, u2, and u3, where these three vectors are below. Here's u1, here's u2, and here is u3. Now you can check u1, u2, u3, they are all unit. They are all perpendicular to each other. And this is the Gram-Schmidt process for this basis B. Next up is number 8. And well, it's very similar to number 7 in that we need to perform Gram-Schmidt. We want to find the QR factorization of this matrix A. Let me go ahead and label the columns V1 and V2. And then let me just remind you, we will find Q, which has orthonormal columns. And then matrix R, we can calculate one of two ways. One is we can keep track of some of the calculations that goes along during the Gram-Schmidt process. Or the other one, we could just take Q transpose A. But maybe I'll do this first because we only have 2 columns in the matrix A. So here would be the length of V1. This is the first entry. This entry is the length of this part. This is the component of V2 that will be perpendicular to the line spanned by V1. And then we have here V2 dotted with U1 and 0. So this is the matrix R that we're looking for in the QR factorization. Now, let's get started on the problem. We begin calculating the length of V1. And then the first vector, just like we saw in the last example, will be V1 divided by its length. We have 25 plus 4 squared, right? Plus 2 squared plus 2 squared. And you see this is 24 plus 25. This is 49. And when we take the square root, we just get 7. Now, immediately, I will erase and put in. We have the first entry of matrix R. It's 7. Okay, wonderful. Now U1, right? This is the first column of Q. We take V1 divided by its length, which we have calculated. And when we do, we just divide, okay, each coordinate by 7. We have 5 over 7. We have 4 over 7, 2 over 7, and 2 over 7. Now let's move on. The next thing we want is to calculate, this is really the direction of the next vector. We take V2, maybe I'll go ahead and write it. This is V2 minus, this will be a dot product, and then times U1, just like we did in the last exercise. So here is U1, 5 over 7, 4 over 7, 2 over 7, and 2 over 7. And then we take V2, which is 3, 6, 7 minus 2. Okay. What goes here is U1 dot V2, or as I have it written here, V2 dot U1. Either way, it's the same dot product. So we are taking the dot product of this vector and this vector. So we have 7 in the denominator. In the numerator, we have 15 plus 24 plus 14 plus 24 plus 14 minus 4. Now, what is this? We have 39 plus 10. Oh, we have 49 over 7. Okay, so this number here, this number is just 7, right? Now, immediately we erase and we have the next, we have the 1, 2 entry in matrix R just through this calculation. We have found this is 7. Maybe I will highlight. So this we calculated is here. It's 7 if you simplify, just as I said. Now, let's just add these two vectors. And this gives us the direction for U2. Then we just divide by the length and we have the second vector. Well, if you just notice, this vector is 5, 4, 2, 2 once we multiply by 7. So here we have minus 2. We have 6 minus 4, which is positive 2. We have 7 minus 2. And minus 2 is minus 4. Wonderful. Now, what is the length of this vector? This is the next step, and we are almost done with this problem. Well, it's a big square root, and we have 4 plus 4 plus 25 plus 16. And well, you notice we have seen the square root before, right? It's here. This is the square root of 49, which is 7. So we have another entry of matrix R. We have 7. So far, the entries of R were here, just to highlight what I'm doing, and then here. Okay. Now, the final step, besides just writing down as a matrix, is we take this vector and divide by its length. So we get U2. This vector is here. It's the component of V2, which is orthogonal to the line and divided by its length. And we get minus 2 over 7, 2 over 7, 5 over 7, and minus 4 over 7. Now, just check, okay? Because if you check this and take the dot product here, we should have 0. If we don't, we have made a mistake. Minus 10 plus 8 plus 10 minus 8 all over 49. Yeah, okay, it looks good. U1 and U2 are orthonormal. My final step is just to write down matrix Q, right? And we have everything. The first column of Q is vector U1, and the second column of Q is vector U2. So we have 5 over 7, 4 over 7, 2 over 7, and 2 over 7. And then the second column, minus 2 over 7, 2 over 7, 5 over 7, and minus 4 over 7. So this is our matrix Q. And then maybe I should color this black. This is matrix R. Here's my final answer for number 8. Maybe before I move on to number 9, I will make a remark. You see, we calculated R by keeping track of the entries that go here, here, and here. Of course, this entry is 0. R is always upper triangular. Okay, and then I just filled it out as I went along. And this is certainly an option. It's the way I did this problem. But you could also calculate R, and we discussed this in class. Also calculate R. This is Q transpose times A. This is just another way to calculate. It's really, either way will work just fine. Fantastic. Well, speaking of the transpose, it is time to move on to number 9. And the question is here. So suppose A and B are n by n matrices. They can be any n by n matrices, do not have to be symmetric. And we need to justify which ones of these must be symmetric, okay? And we have 3 different matrices. Well, I will start with letter A. How do we know if a matrix is symmetric? Well, by definition, a matrix, say M, is symmetric. It means M transpose is M. So in particular, M must be square. This is what we're looking for. So let's just calculate A minus A transpose, and see, do we get this matrix? If not, probably the answer to 9A is no. Okay. Well, when you take the transpose of a sum, we are interchanging rows and columns, or the ij entry of the transpose is the ji entry of the original matrix. And when we add matrices or subtract, it is component-wise. And so the transpose operates like this. We can just take the transpose of each and add them up. Now, one more step, A transpose is always A. So we have A transpose minus A. So we're trying to compare. Is it the case that this matrix and this matrix are always equal? I would say not always equal. So not for A, not necessarily symmetric. If A is not symmetric, this would really be a time where this can fail. So let's just see an example. And this is my favorite non-symmetric matrix. My favorite because it is simple. Sometimes the simplest examples are the best for illustrating something that fails. So my favorite non-symmetric matrix is this one. My favorite non-symmetric n by n matrix is this one. And what happens here? Well, you see A transpose, it just moves the 1 here. And if you take, for example, A minus A transpose, we have 0, 1, minus 1, 0. Then we calculate A transpose minus A. And what do we get? Well, A transpose minus A has a 1 here, a minus 1 here. And you notice these are not equal. So this is a concrete example where letter A fails. Letter B, well, okay, we start the same. We want to take the transpose of this matrix and see, do we get back B transpose? If we do, the answer is yes. This uses, how do we take the transpose of a product? And it goes in the opposite order. So this would be B transpose times B transpose, and B transpose is just B. Oh, so the answer is yes, absolutely. This is always, no matter the n by n matrix B, symmetric. We have, in fact, proved it. Always. One more, letter C. This is kind of similar. We have A transpose B A and take the transpose. Now here, I'm going to group some things. In green, I'm thinking about as one matrix, and here I'm thinking about the other matrix, and I can use my property of how do you take the transpose of a product. This would be BA transpose, and then A transpose. Now, well, I really have 2 steps to take at this point. The first one is now I have another product. I have BA transpose. And so this is just A transpose, B transpose. And my final step here, A transpose is A. This is A. As we did in the first example, we compare these two. And you notice they are not the same. So the answer is not necessarily, again, just like the last one, not necessarily symmetric, this matrix. And if you want an example, well, let's see what fails. In the middle is where we see the difference. We see A transpose, and on the left, we see A on the right. So I need B to be something not symmetric. let's take my favorite non-symmetric matrix, n by n, which is, okay, I used it above. So B is going to be this matrix. And a simple matrix I could justify with would just be the identity, because that's short to do calculations with. Always, when I'm trying to find an example of something that fails, I try to come up with the simplest example I can, just because it makes my life easier. So here, I have these two quantities. First of all, A transpose is A, and if I want A transpose be A, you see I'm multiplying by the identity on each side. This is just matrix B. On the other hand, A transpose B transpose A, well, again, I'm multiplying by the identity on each side. This is just B transpose. B transpose is here. Okay, and you see these are not equal. So this justifies 9, number 9. Number 10, we are given a subspace W of R4. Really, we're given a basis for W. Note that W is a two-dimensional subspace of R4. What we want to do is find the matrix of projection onto W. So this will be a 4x4 matrix. Now, let me just label here. Say I label this V1 and label this V2. You note that V1 dot V2, well, this is 3 minus 3, which is 0. This tells us that this is an orthogonal basis, but V1 and V2 are not unit. So let's first normalize these vectors to get an orthonormal basis for W. Let's calculate the length of V1 and length of V2. Length of V1, you see it's a square root. We have 9 plus 1 plus 1 plus 9. This is square root 20. For the moment, I will leave it like this. Length of V2, well, this is a square root. We just have 9 plus 1. So this is the square root of 10. What I want to do is get unit vectors from vectors V1 and V2. So I can just take them and divide by their lengths. But because I see a square root of 10 here and a square root of 20 here, I'm just going to write this a little bit differently. Let's write this as square root 2 times square root 10. Because what I will do is when I write vector U1 and vector U2, I'm going to leave the square root 1 over square root 10 out in front. This will help me just slightly when I go to find the matrix of the transformation. So here I have 1 over square root 10. And then I have 3 divided by square root 2, 1 divided by square root 2, 1 divided by square root 2, and 3 divided by square root 2. Okay, this is now unit and in the same direction as V1. Okay, U2. Here I'll leave the 1 over square root 10 out in front. This is the length of V2. Then I can just put V2 here. We get 0, 0, 3 minus 1. 0, 0, 3 minus 1. U1, U2. This is my orthonormal basis for W. Now, how am I going to go about finding the matrix of projection? We really have more than one option here. One option, and this would be in the spirit of, say, chapter 2, earlier in the semester, you can project E1, project E2, project E3, project E4, and put those as columns in a matrix. This is the matrix of the transformation. But another way we can do it, and this really uses chapter 5, if I say let Q be the matrix where I put these vectors, this orthonormal basis, as columns. So this would be U1 and U2. Okay, this is my matrix Q. Then the matrix of projection, what I want here is Q transpose. This is what I'm looking for. So this is how I'm going to go about it. And now you can perhaps see why I put this 1 over square root of 10 out in front, because I can just put that out in front of my matrix. So my matrix Q I have 1 over square root 10. Then I put these columns. There's the first column of matrix Q, and then here is the second column of matrix Q. Okay, here's Q. Now I need Q transpose. Well, all I do, I still have the 1 over square root 10 out in front. And then the first column of Q becomes the first row of Q transpose. So this would be 3 over square root 2, 1 over square root 2, 1 over square root 2, and 3 over square root 2. Now, the second row of Q transpose, we use the second column of Q. So this would be 0, 0, 3, negative 1. Okay. Well, before we actually multiply these two matrices, let's just check size. You see Q has 4 rows and 2 columns, and Q transpose has 2 rows and 4 columns. Without a doubt, the product is defined. Moreover, the product is 4 by 4. This is what we're looking for a map that goes from R4 to R4. So let's multiply these two matrices, and then this will be our final answer. The nice thing is, you see I can pull out this constant. Here's constant and constant. Constants can go anywhere. So it's just 1 over 10. All out in front, 1 over 10. Now I will have a big 4 by 4 matrix. To get the first row, okay, I'm taking this first row and dotting it with each column. And you can see what I get here. I get 9 over 2. I get 3 over 2, 3 over 2, and 9 over 2. This is the first row. Now I have 3 more. To get the second row, I take this and I dot it with each column here. So you notice I get 3 halves. I get 1 half, 1 half, and 3 halves. The next row, you see I have 3 halves. I have 3 halves. And then I have 1 half plus 9. Well, 9 is 18 halves, so this will be 19 over 2. And then the last one, I have 3 halves minus 3, which is 3 halves minus 6 halves. This one is negative 3 halves. One more row, we have 9 halves. We have 3 halves. Now, 3 halves minus 3. Once again, this is negative 3 halves. Then we have 9 halves plus 1, which is 11 halves. So this is okay for a final answer. You know that you could also just pull this 2 that's in every single denominator out in front if you wanted to. Maybe I will mention that as an option. I could write this as 1 over 20 times this matrix, which has all integers. There's nothing wrong with the matrix I have above, but this is just another way to write our final answer. You see it's 1 over 20, and I have 9, 3, 3, 9, 9, 3, 3, 9. Then I have 3, 1, 1, 3, 3, 1, 1, 3. I have 3, 1, 19 minus 3, 3, 1, 19 minus 3, and I have 9, 3 minus 3, and 11. Okay, so this is, either way, it's the exact same matrix, just 2 different ways of writing it. So this is our matrix of projection onto this subspace. You'll notice this matrix is symmetric. Necessarily it would be. And we also know, for example, this matrix will have rank 2 as the dimension of my subspace. I have the true false grouped into 2 groups of 4. So let's start with A through D. The first problem, there exists a 4 by 3 matrix A such that the kernel of A equals the image of A. We really need to use rank nullity here, or that's one way to go about it. It's the way I will think about it. Because we know the dimension of the kernel of A plus the dimension of the image of A is the number of columns, which is 3. Now, if these 2 subspaces are actually equal, then they have the same dimension. So for example, we would have to have 2 times the dimension of the kernel of A equals 3, and no subspace has dimension 3/2. So this cannot happen. This is false. And make sure when you're taking a test that if you write F or if you write T, make sure I can tell the difference, because if I can't, I've seen a lot of in the past things like this for answers. That's just wrong, no matter what you thought you were putting, because I can't tell the difference, but I'm grading it. Okay, very nice. We move on. Letter B. If A is an orthogonal matrix, then A transpose is an orthogonal matrix. Well, this is a fun question because we have multiple ways to think about orthogonal matrices. First of all, they are n by n, and their columns form an orthonormal basis for our n. Now, another characterization is the following, and this might be the way that I think about this problem. We have that A transpose A is the n by n identity, and A is, of course, square. Okay, this is equivalent to being an orthogonal matrix. Now, if you go back and think about our criterion for invertibility, I have two matrices that are both n by n and multiply to be the n by n identity. So immediately I know that A transpose is A inverse, but I also know that if I multiply in the other order, I also get the identity. So I also get that A transpose must be the identity. And now I can just rewrite this. Rewriting A is in fact A transpose, and then I have A transpose, and this is the identity. So you notice this equation, as I was saying, for an n by n matrix A is equivalent to being an orthogonal matrix. But now I have this exact equation, but instead of seeing matrix A, I see matrix A transpose, right? Here's A transpose, transpose, and then times A transpose, and this is the identity. And this gives us A transpose is an orthogonal matrix. It's one way to think about this question, at least. B is true. Now letter C. If V is the span of V1, V2, V3, then the dimension of V is 3. I will just say no, this is false. And I can give an example. For instance, if you take 1, 1, 1, 0, 0, 1, these span, it's 3 vectors, and they span R2. But the dimension of R2 is not 3, so this is false. There is a true statement if you change it. If this just said less than or equal to instead of equals, it would be true. But as written, it is a false statement. Okay. Very nice. Letter D. If V1, V2, V3, that collection is a basis of V, and, well, before I even read the and, let me tell you what I can get from this first statement. Immediately, I see the dimension of V is 3. Okay? That comes from this, because I know how many vectors are in a basis. Now, also I am told that this V is the span of 3 potentially other vectors, W1, W2, and W3. And then the statement is that that is also a basis for V. So this is true because we, starting off, we know the dimension, which is 3, right? We know the dimension of our vector space. And so any 3 vectors that span are a basis for V. Equivalently or similarly, you could say any 3 vectors that are independent will span V. Once you know the dimension, and we have discussed this, but this is part of the review, once you know the dimension, you either need to check one. Of course, you could check both span and independence, but you only need one to guarantee that you have a basis. So this is a true statement. Okay. Now let's move on to letter E. If A is an n by n invertible matrix, then the dimension of the image of A is 0. Not unless n is 0, and I'm not sure how to interpret a 0 by 0 matrix. So I will just say the answer is no. What is true is the dimension of, for an invertible matrix, the dimension of the image of A is n. Okay, the columns of A will be a basis for Rn if you have an invertible matrix. And so this is a false statement here, letter E. If A is an n by n invertible matrix, then the kernel of A to the 10th is the 0 subspace of Rn. This one is fantastic. If you have an n by n invertible matrix, this will imply that any power, say A to the 10 or A to the 100 or A cubed, something like this, will be invertible. Therefore, the kernel, well, the kernel of an invertible matrix, this is rank n. It is just 0. And so the 0 subspace of Rn, fantastic. This is true. Now for G, we have an 8 by 9 matrix with rank 8. And the question is the dimension of the kernel 0? Or it's a statement, and then we decide if it's true or false. Well, we have to pay attention to the number of columns here. We have 8 rows, we have 9 columns. And the dimension of the kernel, this again is rank nullity. The dimension of the kernel of A will be the number of columns minus the rank. And this is 1, which is not equal to 0. So this is a false statement. We are on letter H. For any two vectors u and v of Rn, if you take this length squared, length of u plus v squared, this equals the length of u squared plus the length of v squared. Well, we will see, or I can just say this is false. We discussed, in fact, this holds if and only if u and v are perpendicular. Okay, you can think here, this would be length of u, length of v, and then this is u. Oh, I'm writing it the other way, but it's fine, u plus v. And it really comes from a right triangle, a squared, here's the length. Okay, a squared plus b squared is c squared. So to find a place, well, that would be justification that it happens if and only if u and v are orthogonal. But I'll just give a specific example, and I can create a simple one here. Okay, where it fails, all I have to do is take 1, 0 and minus 1, 0. Okay, this will be, for example, here's my u and here's my v. I'm just trying to find a simple example where this fails. And then here is u plus v. And you notice, for example, all these quantities, the length of u equals the length of v, which is just 1, and the length of u plus v. Oh, I should square it, and it's still true what I said. I'm just trying to match this. You take the length squared, and we still have 1. Very nice. The length of u plus v squared is 0. And, well, of course, this is not equal to 0. So this is justification, but also you could just make a statement about perpendicular vectors. This is just an example. And this is the end of this test review. Thank you very much.